To pick up where we left off yesterday, we were somewhere talking about angular and linear velocity. We're just kind of getting started. Do you remember where those buttons are for degrees, minutes, and seconds? Okay, it's under the angle menu. And then where's the little quotes if you're going the other direction? Yeah, the home screen there. Okay. 5 and 6. All right. We started talking about this, and I'm just going to go over this a little bit more. There's some formulas here, and all the formulas, guys, are on the peach sheet. I think they're on the side that has the unit circle, right above the unit circle. Do you know what I'm talking about, that peach reference sheet? Okay. Basically, you might just want to have that on your desk most of the next 9 weeks. So, at the top above the unit circle are the formulas that have to do with these. Okay. So I don't ever use this formula. Linear velocity uses this. I do use the formula, I just don't think about it as a formula because I know linear velocity means I need some kind of distance divided by some kind of time. So then I just look at what they've given me and I find the distance and the time and divide them and I have the linear velocity. Okay. Angular velocity, on the other hand, has to be in radians per time, and the angular velocity is this W-looking thing. And we talked yesterday about some sample relationships. Now, there's one more that isn't given right here, that if you know the angular, or you can find the angular velocity, if you multiply it by the radius, you'll get the linear velocity. And the reason for that is if you have radians per time and you multiply it by some distance, then magically the radians go away and you just get a distance per time. Did we talk about that a little bit yesterday? That radians really isn't there? All right. Then we went through this example that was already done for all of you. And the big takeaway from this example was that revolutions, well, it's important and we need to know it. It doesn't actually go into any of these formulas, right? They only work with radians. So we had to convert revolutions. We could say 1 revolution is 2 pi radians. And then we had some kind of radians to work with finding angular velocity. All right. What did this want? Oh, this was a weird question. Find the rotation in revolutions per minute. That's probably not on a quiz, so I'm going to skip that. I know it's not on a quiz. Okay. Number 7, find the radius given the linear speed and the rate of rotation. Again, this is kind of working backwards. You want to do 7 or 8? Okay. I don't honestly think this is on a quiz either, so we might have one on the homework, so we'll do one of these, but it says something is turning 120 revolutions per minute, and we're given a linear speed of 24.8 meters per second. Okay, we got a mess. Do any of these labels match? No. Do you want to change? Let's change this to seconds. Would that be okay? How would you change this to seconds? Yeah, we need minutes to go away. So dimensional analysis says we need it on top. And minutes and seconds are related. And then you have to say to yourself, okay, what do I know about these? Well, 1 minute is 60 seconds. So if we do that, we get 120 times 1 divided by 60, or 2 revolutions per second. What did I say about revolutions? Useless in all these formulas, right? So we need to change this to radians. And we need revolutions to go away. And what do you know about revolutions and radians? Okay. 2 pi radians is 1 revolution. Everybody good with that fact? Okay. Revolutions cancel. We end up with 4 pi radians per second. Okay, what kind of unit or what kind of speed is that? Angular or linear? It's angular speed, okay? The linear speed we were given up here is 24.8 meters per second. Anybody know the relationship between those? I just wrote it down a minute ago. We're trying to find the radius. It's an important one that's on your peach sheet. By the way, if you want to write on your peach sheet, you can, because I have a blank set that I'll use for quizzes and tests. Does that make sense? So if you want to write something on there, go ahead. A linear velocity equals angular velocity times radius. Do you remember where I wrote that one a second ago? Okay, so what are we going to do with these? If we have a 24.8 over here, yeah, and a 4 pi, oops, I can't write, that says 4 pi radians per second. So we need to divide or multiply by the reciprocal, okay? So type 24.8 divided by, now this gets a little tricky. If you type 4 pi on your calculator, is that going to work? Why not? Because it sounded like it when Hofbauer said it, right? Does anybody know why this isn't going to do what we want it to do? What is the order of operations going to do? Well, it's going to go left to right. It's going to divide by the 4, but then it's going to multiply by the pi, right? And we need the whole 4 pi to be divided into here. So on the calculator, you could type 4 pi and get a decimal first, absolutely. And then do 24.8 divided by that decimal. But if you wanted to, was it 24.8, guys? Is that what I just said? Yeah. Divided by, if you want it to divide by both the 4 and the pi, you got to put them in parentheses. Or like I said, you could just do 4 pi and then say, wait a minute, I need 24.8 divided by that previous answer. Okay, so we get 1.97. And what labels were left? This was meters per second, and we ended up multiplying by the reciprocal, which was seconds over radians. So what was left was only what? Yeah, but radians just go away, so this is meters. Ugh. Right. Once again, there might be one on the homework, but that's not on the quiz. The ones on the quiz are almost all straight up application problems, and here's an application problem. It says a curve on a highway has a 1,000-foot radius with lanes that are 14 feet wide, each lane, okay? If the curve makes a 180-degree turn, how much longer is the outside edge of the lane than the inside edge? So you're driving down the road and the road takes a big curve. It's always faster if you're on the inside, right? Because you travel less distance. Okay, so we're going to figure out how much less. So we're going to, it's kind of unclear what distances they want us to use. So what I decided is we're going to talk about the very inside and the very outside. So if you were like riding a bike down the inside line or a bike down the outside line, how much further would you go, okay? So what we really want to find is this distance. What is that called? Straight up distance around the edge of a circle. It's a part of the circumference. Do you remember what it's called? Arc length, okay? We want to find the arc length and the difference in those. What's the formula for arc length? Anybody remember? Good job. And what does theta have to be in? Radians. So we know we're talking about a half a circle or 180 degrees. So we need what? How many radians is 180 degrees? Is he right? I hope you know that much, right? Halfway around the circle is halfway around 2 pi or 1 pi. So the arc length on this picture is S equals pi times, that's because pi is theta, the radius of 1,000. And the arc length on this one would be what then? Pi, which is the theta, times the radius of 1028. I did that backwards. I did theta r instead of r theta, sorry. And then we want to know how much longer it is. So what do we want to do? Subtract the difference, which would be, anybody? 128 pi minus 1,000 pi would be a difference of 28 pi, or anybody got an answer for me? 90, 80, something? Roughly 88 feet further. So it was 1028 pi minus 1,000 pi was 28 pi, or about 88 feet. Because I just typed 28 times pi. Are we all good? Some of you are looking kind of confuzzled. All right, 6a. This is another formula that deals with the same concepts of, basically this section is all about the crazy formulas that use radians. This one talks about a sector of a circle. A sector is like a wedge. So your mom bakes you a round birthday cake and she cuts you a big chunk, okay? How much area of frosting on the top? So it's the area within that wedge of the circle. And the formula, area of a circle is pi r squared, right? But this is in, we're going to use radians. And so we're going to have 1/2 r squared theta to find the area. All right. So Jaden is planting a circular garden in her backyard with a radius of 10 feet as shown below. What area does she want to use for tomatoes? Okay, tomatoes it says is what? 50 degrees. Can we use that in this formula? Okay, to use this particular formula, 1/2 r squared theta, we need radians. So how do we change degrees to radians? Okay, a little dimensional analysis. 180 degrees is pi radians. The degrees cancel. So now this is theta. Now what? We have to take theta times 1/2 and times r squared, right? I'll rewrite it. Some of you are looking confused. What's the radius? Yep, it said right here, radius of 10 feet. So we have 10 feet squared times 50 pi over 180, which you could have reduced or gotten a decimal for. And that's going to give us our area. And what label are we going to have? Feet squared or square feet? Yep. So, yes. No, you should be fine as long as you use a long enough decimal. Okay. So 1/2 of 10 is 5, 250, 25 over 18 times pi. Yep. Anybody got an answer for me? I think the exact answer is this, but I would rather have a decimal anyway. Sounds right to me. Thanks. And that's square feet. Probably 4.5 or 4.4 square feet, just so we know a rough estimate of what we're talking about. Okay, what does she want to use for wildflowers? Just ask us to go back and look. Wildflowers is 80%, so, or 80 degrees, I'm sorry. So it's 80 times pi over 180 to get it into radians. And then the formula is 1/2 r, which was 10 squared, times theta. Let's see, 10 squared would be 100. Half of that would be 50. Yeah, I don't know what that reduces to. 20/9? No. Anyway, can anybody just give me a decimal? Is it reduces to 4/9? No, no, no. I meant the whole thing after we typed it all in. You know what? Okay. This isn't the right answer, though. Does anybody know why? She's going to put wildflowers here, but she's also going to put... Yeah, we got to double it because it was 80 degrees on this side and 80 degrees on that side. I didn't notice that. Yep, we can double the final answer. Is absolutely right. What'd you get? Is that not what you got? Or you doubled it now? Okay, so around 140 square feet. Did anybody else get that? No? I didn't do any typing. Okay. If 6 ounces of wildflower seed can cover 10 square feet, how many ounces does she need in order to plant all the wildflowers? Okay, so she's planting this many square feet of wildflowers. And what are we going to multiply maybe? We need square feet to go away, and we need to end up with what? How many ounces? What do we know? So 6 ounces can cover 10 square feet. So now the square feet will divide away, and we need to do 139.6 times 6 divided by 10. Anybody else get that? So around 84 ounces she would need to buy, depending how it comes. You're good. Half of 10 is 5 times this is 2. Oh, I didn't square it. This is he right, guys? Is this 43.6? Yeah. So was it? I don't think it was 25 pi over 9 then when it reduced. Yep. If you're watching the video, don't listen to me. What was it? 43 square feet? That makes more sense. I was trying to figure out how this got so much bigger. This one was? Well, this would simplify to 5 over 18. And then this would be 100. Half of that would be 50. So I think it's 250 over 18 instead of 25 over 18. It doesn't matter. Is anybody going to go out and talk about their square feet in terms of pi when they measure in their garden? No. So my doing an exact answer was useless. Somebody confused? All right. This is, well, there will be probably one arc area of a sector, question on the quiz. There's definitely going to be a question about angular and linear speed as well. Okay, so this would be an application question that could be on the quiz. One type of wind turbine blade is 27.1 meters long. What is that? Yes, if you have a blade, a single blade here of something that's turning, this is the radius, is 27.1 meters, okay? It is rotating at 28.5 revolutions per minute. Well, we discussed revolutions is useless to us, except it tells us how to get what? So we need to get rid of revolutions, and 1 revolution is how many radians? Revolutions will cancel. 28.5, 57 maybe pi. If you double 28.5 to get 57. So we have radians per minute. Is that something we needed? What is radians per minute? What does it mean when you have radians per minute? It's a speed. It's a speed of what? Yeah, well, it's, we think in revolutions per minute how many times it's turning, but this is how many times it's turning in radians. So it is an angular speed, okay? So when it asked up here for the angular speed, this is the angular speed, which that's the letter they use, but let me just write angular speed so you remember that. So we found that. Now, how do we find the linear speed? Do you remember at the beginning of the hour I said this is the relationship you're going to use most often? So we got to multiply that 57 pi by what? Yep, by 27.1 meters. Miraculously, the radians just go away. And we get meters per minute. I didn't leave myself room there. 57 times 27.1 and times a pi is going to be a big number. $4,852 roughly. Okay. Round to the nearest tenth. Okay, someone else get that answer? And that is meters per minute. And it didn't tell us. Sometimes it'll say in the directions, like it wants it in meters per hour or something different, but this one didn't say, so I'm going to go with the easiest label, and that's it right there. They don't tell us we have to convert. I'm going to leave whatever labels they give us. So this was the angular speed, and this was the linear speed. All right, now we have a centrifuge machine that spins real fast to separate fluids. Has an angular speed of 400 pi radians per second. They actually gave us the angular speed. Only now they want us to go backwards and find rotations or revolutions. So it's right now 400 pi radians per second. And they would like us to change it to revolutions per minute. Just a dimensional analysis question. Christian, tell me one thing to change. Okay, so if I put seconds on the top, what'll I have? There's 60, so where do I put the 60? Good job. 60 seconds is 1 minute. Now seconds cancel. I want revolutions. Keaton, can you tell me how to do that? Okay, because I need the radians to cancel, and 2 pi is 1 revolution. So for this one, I needed the 2 pi on the bottom. This is another one of those questions where you would need parentheses to keep the 2 and the pi together. But can we just do part of it in our head? How many times does 2 pi divide into 400 pi? And then we had this 60 in here. So 200 times 60 is 12,000, right? Did I do that right? And that's RPMs, revolutions per minute. What is the linear speed if it is 8 centimeters away from the center? Okay, linear speed. Well, which one do we want to use then? Which of those speeds? RPMs or the original radians per second? Yeah, because our formula for linear speed that I like to use uses angular speed that's already in radians. So 400 pi radians per second times 8 centimeters will give me 3,200 pi, or can anybody tell me a decimal approximation for that? 10,000, 9,000? Okay, and that would be what label? Centimeters and seconds were our labels yet. Any questions? All right. Did I go too fast? Did someone need? Everybody okay? All right. A flywheel mounted on an engine crankshaft has a radius of 6 if it's running 2,800 revolutions per minute. RPMs means revolutions per minute or rotations per minute. You can think of it the same way. What is the linear velocity on a point on the outer edge of the flywheel in feet per second? All right. This is a quiz question, something like this. What do we know to start with? Anybody tell me where to start? Okay, we can write the radius is 6 inches. What else do we know? 2,800 RPMs, or rotations or revolutions per minute. Okay, I want a linear velocity, so I'm going to end up using this formula, but do I have an angular velocity yet? I don't know about backwards. No, if we divided, if we divided by 6 inches like this, you'd have minute inches in the denominator. That doesn't make any sense. Is this an angular velocity, guys? Yes. We need to make this an angular velocity by changing it to what? Radians. That's it. So 1 revolution is 2 pi radians. Revolutions is gone. I have 5,600 pi radians per minute. And now that's what? Angular. That's your angular velocity, which is going to go in here. And then we're supposed to multiply by what? R, which is 6 inches. Before we stop writing, though, we could calculate this out right now, but is it going to be what they want? What do they want? Feet per second. So can we go ahead and keep going and change that to feet per second? We need a couple conversions in here. Right now I have radians, which are going to just go away. I want to get rid of minutes. Can you help me get rid of minutes? 1 minute is 60 seconds. Okay. Now I have seconds, but I don't want inches. I want what? Feet. So what am I going to do? Okay. I need to get rid of inches and wind up with feet, and the conversion is 1 foot is 12 inches. Yes. Absolutely. Absolutely. It doesn't matter what order you do the process in as far as typing it in separately. I usually just go all the way across the top first and then all the way across the bottom, but you can do it as separate division problems. If I do the top, I have 5,600 times 6 and times pi. And then the bottom is 60 times 12, which is 72, 720. Okay, I did the bottom right. Anybody got the top for me? 5,600 times, what was it? 6? Okay, that's 33. I didn't put the pi in yet. Okay, so now if you type it all in and give me a decimal, anybody? Did it have 2 zeros or 1? It had 2, right? Okay, times pi. And then divided by 720. 146.6, okay? I could have done 5,600 pi times 6 inches, okay? Gotten that answer. and then said I need to divide by 60 to change it to seconds, and then I need to divide by 12 to change it to minutes, and I still get the same answer, okay? 146 point what, guys? And it was feet per second. All right. A lot of steps to getting that guy, but most of it's just dimensional analysis. We good? Are we finally done? Okay. So now you can finish up page 238 and the word problems that are on the front of worksheet 7. Somewhere on 7, you just have to do 3, 4, 5, and 7. Now, the rest of the hour, we're going to talk about the unit circle, which is on the back of this. You have a unit circle on the back of 6? Okay. There's also a unit circle on the back of 10, maybe? Those are there for you to practice, okay? Because you have the memory quiz for the unit circle on Friday. I'm going to go through and talk about how I do the unit circle to remember it easily. If you haven't had this since Honors Algebra 2, we need to talk, okay? We need to think about how these all come about. And if you've already just had trig, I would like this to make some sense to you, okay? How you do this. And so just follow my, watch me here for a second. This is 0 and this is 90. I don't think I'm giving you any news there, right? Halfway to 90 is this guy, which is 45. Okay? And then we split it. We have the 30, 60, 90 business, so we have the 30 and 60 in there. Now, this amount of turn right here, everybody see what I'm talking about, is 30 degrees. This amount of turn is another 30 degrees. This amount of turn is another 30 degrees, right? So if you wanted to, if you don't have them memorized already, you could take this 30 and go all the way around. 30, 60, 90, add 30, 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 add 30. To get all those, okay? And then if you were doing the 45s, so you add 45 once and you get 90, add 45 to that and you get 135, add 45 to that and you get 180, add 45 to that and you get 225, add 45 to that and you get 270, add 45 to that and you get 315. The degrees are usually the easiest part. Most of you memorize the degrees pretty quickly. Did I mess anything up, guys? By the way, the actual unit circle quiz also asked you to call this both 0 and 360, I think. All right? We good? Now, converting those to radians becomes a fraction issue for most students. Remember, 180 degrees over here is pi radians. So if I cut it in half up here, I'm at pi over 2. If I cut that in half again, I'm at pi over 4. Okay? Or if I take 180 degrees and I want this little wedge right here, if you divide that by 30 degrees, you get what? 180 divided by 30 is 6, because this is 1/6 of the way over there. Now, I just start with this and I go around by 6 to save my time and effort. So this is 1/6. Remember we were doing these guys? We said the next one is 2/6. What's 2/6 reduced to? Yes. Then this one would be 3/6, which is 1/2, which is already there. The next one would be 4/6, which would reduce to what? 2/3. The next one, and we're skipping the 45 in here, but the next one is 5/6, which doesn't reduce. Then we have 6/6, which is 1. The next one is 7/6, which doesn't reduce. We're skipping the 45. The next one is 8/6. Does that reduce? 4/3, right? 8/6 reduces to 4/3. The next one is 9/6, which I didn't write down yet. Some of you might already know that one, but it is 3 pi over 2. The next one is 10/6. What does that reduce to? And then the next, we're skipping the 45, and then we have 11/6, which doesn't reduce, right? And then we'd have 12 pi over 6, which is 2 pi. So we had 0 radians, pi over 6, pi over 3, pi over 2, but we really did it just using the 6th, right? Okay, now we can do the 4th. We had this guy was a pi over 4. 2 of them, well, it's already reduced to pi over 2. So then this is what? 3 of them. 4 of them, well, 4 pi over 4 reduces to 1. Okay. Then we have what down here? Okay, what we're doing is we're talking about this much change right there. 1, 2, 3, 4, 5/4. 6/4 would be here, which we already have. And then this one is 7/4. It's supposed to say 7 pi over 4. And then 8 pi over 4 would be 2 pi. All right, do you feel like you can do the degrees and the radians? Yes. Okay. That's the one you start with, so that may be the one that you need to memorize, but it was 30 degrees, and so it was this part of pi, which is 1/6. Because pi is equal to 180 degrees, so I just did 180 divided by 30 degrees would be 6 times it would go in there, so it's pi over 6. Does that help you see where it makes sense? But thank you for asking, because I'd rather some of this made sense to you. All right, guys, this is Hofbauer's way of doing it, and then I got some little cheater ways, okay? I just memorized this ordered pair, not in the order it is, but the fact that I needed a square root of 3 and a 1/2, a square root of 3 over 2 and a 1/2. So then what I do is just look up here for a second, okay? I just go, well, I went over a lot further than I had to go up. Does that make sense? On this first 30-degree ordered pair right here, I had to go over further than I went up. So square root of 3 over 1 up. They're always over 2. Okay. If you were doing a special right triangle, this would be 30, 60, 90. Okay. And the short leg is x, the long leg is 2x, and this is x square roots of 3. But what you actually end up doing is dividing everything by 2. So the up is the 1/2. The over is the 1, which turns out 1. And this is square root of 3 over 2. All right, if you can get that point, you should be good. Now, that point repeats. So this is square root of 3 over 2 and up 1/2. This one is the same point, square root of 3 over 2 and up 1/2, except I went left, so which one's negative? The x. This one down here is square root of 3 over 2 and 1/2, except I went left and down, so they're both negative. And where's the other one that's exactly the same? Do you see this little bow tie, guys? I went 30 up, 30 up, 30 down, 30 down. So it's this one, square root of 3 over 2 and 1/2. But this time I went to the right and down, so the 1/2 is negative. All right. Going back here, when I do the 60, okay, when I do the 60, I'm going over less and up more, right? So I am going over the 1/2 and up the square root of 3 over 2. So now I go around and do those 4. Where are those 4? Well, over 1/2 and up a square root of 3 over 2. is 60 degrees right there. Over here is the same thing. Okay, should reflect. If I fold my paper in half, it should match up. 1/2 square root of 3 over 2. But this time I went left. Down here, it was over to the left 1/2 and down square root of 3 over 2. So they're both negative. And over here, it was left 1/2. I'm sorry, right 1/2 and down square root of 3 over 2. Almost put my sign wrong there. That one should just be +1. All right. Anybody remember what 45 is? Yeah. A 45, 45, 90 is exactly the same, right? The rule we learned in geometry was this. But if we want this unit, the radius, to be 1, we have to divide everything by square root of 2. So that becomes 1 square root of 2 over 2, square root of 2 over 2. So the ordered pair here is the same amount over as it is up. So what are we going to do on all these? They're all square root of 2 over 2. Square root of 2 over 2, square root of 2 over 2. Stays both positive in the first quadrant. What happens in the second quadrant? We went to the left. Honestly, signs are what students usually get wrong, and I just want to kind of cry. Down in quadrant 3, we went left and down, so they're both negative. To the right, we went right, and then we still had to go down. All right. It is a unit circle, so on the circle, the radius is what everywhere? The radius is 0? The radius, this length, is 1, so this is over 1 up 0. What about up here? Over 0 up 1, and I have to say the words or I will get those backwards every time. This one is left 1 and up 0, and this one down here is over 0, down 1. All right. Anybody know some of the cheater methods? There is a method that they use. You use your fingers. I have to demonstrate this with the board. Put your left hand up here like this. Okay. I put this finger down. So it says there's 3 and 1, right? So this is square root of 3 and 1. If I go to the next one, I put this finger down and I have what? 2 and 2. So this is 2 and 2. If I go to this one, I put this finger down and I have 1 and 3. Does that help anybody?
I like the way you did it.
I like the way I did it because it makes sense to me. I can always check. I went over further and up less. So I got the square root of 3 and 1. All right, the other things you need to know, guys. What is x? Cosine or sine? X is cosine, y is sine. Okay? And their sign values. This quadrant, everything is positive. Which ones are positive over here? Y values, which would be the and the cosecant, right? Okay. Down here, no, they're not all negative. Because tangent is y over x, right? So tangent is positive down here, and it's reciprocal. Oh, this board isn't. And over here, cosine is positive. Learn it, all students take calculus, maybe? Okay. So that's also on the unit circle and asked about sine. We'll practice it tomorrow. Everything. And we're memorizing unit circle. The unit circle quiz is this Friday, yes. This is the assignment you should be working on. Yes, that's it. 10 minutes. Who's on your shirt? Is that Bryson? Because he's like your idol, or?
Got hit
Gotcha.
I